In 5.3, they're just giving another example. This is just another example of how this design process that we've been studying can be applied on paper to a real-world problem, a real-world design. In this particular case, the space shuttle, right? So the space shuttle was a very unique space-going craft in that it was very large. It was the largest thing that we've ever sent into space, the space shuttle. And another great thing about it is that because it was so large, it could carry very large objects into space. For example, the entire International Space Station was carried up piece by the space shuttle, as well as some very large satellites and other things that are very difficult to send into space now that we don't have the space shuttle program. But in order to get these things out of the space shuttle is essentially just a big open bay for these objects that would carry into space. In order to get it out, they had to build an arm that could grab onto things and move them out. So one of the requirements for this robotic arm was that it had a hand on the end that could grip something, and they, being the NASA and also the company from Canada that built it, put together a matrix, probably looking a fair amount like this, that helped them decide how they were going to build and design this thing, right? They had a list of properties that they wanted this robotic hand to have, and they're specifically talking about robotic hand actuators. So the thing that actually makes the robotic hand move, close, grip, so on and so forth. So the first thing was that it had to have a soft grip. Okay, we don't want to crush anything. So the weighting factor for that is 10. In other words, that's the most important thing, is that it has a soft grip. And the failure of this grip, if the grip fails, if it breaks and doesn't work properly, it should not damage the space station or the shuttle. So those are the two most important things. They're both rated at a 10. The next most important thing down the list here is the reliability, 9. Right? 9, a failure could cause a mission to be scrubbed, which is very expensive. We don't want a failure of this thing to completely screw up the mission. Okay? Maybe that means that it can be fixed in space. Maybe that means you can replace it, bring a backup, or something like that. But it shouldn't scrub a mission. Okay? After that, we have a number 7 here, compatible with vacuum. In other words, it needs to be able to work in the vacuum of space, and it needs to be able to work with vacuum parts. Okay? That's a 7. Then they have 2 6s, the cost and the time schedule. And then they have 2 5s, at energy efficient and mass. Right? 3 5s, operates over full temperature range. So they've got these different things that they want to achieve, but the importance of achieving them is different for each thing. Some of them are absolutely essential, some of them are not so essential because you can work around them, right? That is where they get into this identifying constraints and criteria for success, right? This is their evaluation matrix for deciding what is going to be a successful robotic arm actuator, hand actuator. And then they start coming up with some ideas for how to make these robotic hands. Right? One of them just has 2 pieces, and the 2 pieces are linked to an arm here, linked to the arm this way, and you pull on this cable back here. The actuator is some kind of, maybe it's a pneumatic actuator, maybe it's hydraulic, maybe it's electric, electromagnetic, whatever. But it pulls backward and it tightens up these 2 cables, which is going to open up this grip. And then if it pushes forward, it pushes on the 2 arms and closes on the grip, right? And we've got some detailed drawings over here, some more detailed drawings. And then we have a different one here where we have a fixed arm, a fixed part of the hand that doesn't move, and one part of it that does, right? And then the actuator is back here. And then they go into a more detailed schematic of how the actuator works. So we have three different types of actuators: a pneumatic actuator, and the pneumatic actuator is using some pneumatic symbols that you probably are not familiar with, things like pumps and flows and things, but you don't need to be familiar with them. This one is a pneumatic actuator. This one is a hydraulic actuator. So this one uses hydraulics. This one uses air. This one uses oil, liquid. And this one here is an electric motor actuator, where you have a motor here that's turning a screw drive, and the screw drive is connected to some worm gears, and that's going to close and open the arm. And they start writing down some information about the advantages and disadvantages of these different studies, right? So they're starting to analyze the feasibility of these studies. They analyze them for every category. They analyze them for the soft grip, the failure does not do damage, energy efficient. They go through the whole thing, and then they rank them, and this is the table that we're interested in. Okay? So we've got option A, option B, and option C. Soft grip, the weighting factor, and the score. The score and the weighting factor are multiplied together to give us a weighted score. So option A gives us 100 on the soft grip, and 80 on the failure, and so on down the list for a total score of 425 as it gets analyzed. Right? Is this completely subjective or completely objective? Are there going to be kinds of opinion things maybe evaluated here? Yes. But there will be some things that we can definitely measure and give a more objective score to. And hopefully our subjectivity and our objectivity will cancel out. But we have also these other two that are being evaluated. It turns out that option C has the highest ranking of all. Right? And that would be, in this case, the electric motor, which is what they went with in the end. The electric motor is very simple, doesn't have things under pressure. It's not likely to fail because it doesn't have things under pressure. Works in all kinds of conditions and everything else, so it's great. So the end result being, and the feasibility study told them that the fixed arm with the one moving part was best as well, because fewer moving parts the better, right? And then they used a screw drive on the end of it as the actuator, and that was the final design. Now, hopefully we've been able to demonstrate to you or show to you how when we spend more time on paper and more time calculating and more time evaluating and more time writing things, we spend less time screwing up in the end, right? And that's really the entire purpose of having an engineer. Okay, I've been working on building an addition on my house for a couple of years now, and almost all of my work that I've done has been on paper. So far, the only work I've really done outside is to dig a hole and fill it with concrete. Okay? In 2 years, all I've done really is build the foundation. And on paper, I've gone through plan after plan after plan for building this house in a way that my wife likes it, in a way that it's going to be strong and look good and be functional and be affordable. I've probably planned it at least 20 different ways. I've done 20 different plans, and I finally have a plan that I think is done. And I will get started on hopefully this coming year. But because I've been patient and worked it out on paper and talked with people that know, and I've evaluated and analyzed things over and over again and redrawn and redesigned and gone back to the drawing board so many times, I have spent a lot of time, but I haven't spent a lot of money. I've spent just a couple of $1,000s on concrete, and I've not even a couple of $1,000s, probably about $1,000 on concrete, and just a lot of time, just a lot of free time on my own doing feasibility work, doing planning work, doing design work, okay? And in the end, it'll probably cost me a total of about $20,000 to build, but that's way better than the $50,000 that it would probably cost if I just started building. And I tell you, that's true. It's absolutely true. I've known many people that have just gone off and built, even people that are very experienced builders will spend more money building than an experienced engineer who spends more time planning. Builders are not very good at saving money. In fact, they're really bad at it. Okay, unless they've got experience with planning, which some builders do, some builders don't. But it's the planning that saves you the money and the resources more than anything. My brother-in-law is one of these. He has a degree in building construction management or something like that, and he has spent his entire career essentially managing buildings. You know, a big building that has this, heating system, this other system, and this other system. So he manages these buildings and makes sure everything's running, and manages a project to make sure the project gets done, and add on or whatever else. But he's never been in the design field ever. And he decided he was going to do an addition on his house, which is smaller than the addition on my house. And he just jumped into it. He took out a huge loan, I don't know, $50,000, $60,000, and he's going to spend it all of it, on an addition half the size of mine. And he's probably almost spent all of it already. It's my opinion that he'll never finish his addition, that it will be half-baked and half-finished for a long time, because he'll just run out of money. And since he took the loan out on his original house, he can't take out any more money, because he's essentially taking out a loan on a house that he's rebuilding. He has to finish the job for the house to be worth anything, in other words. So it's very important as engineers that we plan. Way easier than spend, run out of money. Much better, much easier to recover from. So our next project is going to be plan. Let's go find our next project. Where is it? Here it is, page 23. Beware of slow-moving vehicles, right? Using the material supply, build a scale model vehicle that will travel at the lowest rate of speed possible. When completed, your vehicle will be tested on an elevated platform. The successful vehicle will be the one that travels continuously for the greatest amount of time without falling from the elevated table surface. This will force you to consider gear ratios, distance, guidance, and speed. Okay? Design criteria. Design teams must use only materials and tools supplied at the beginning of the design challenge. I haven't shown you my picture. I may show you my computer here so you can see what I'm looking at here. So here are the design criteria. You can only use the materials and tools supplied at the beginning of the design challenge. Again, I've provided you with materials, and those are the materials that you will be allowed to use. Completed vehicle must, and also, you want to use as few of them as possible, just like on every design. Every design that you do in this class will be graded on the amount of materials you use. The more materials you use, the more expensive the design is considered to be. So the less efficient of a design it will be. The completed vehicle must operate freely without human intervention once movement has begun during testing. In other words, once you've started it, you may not touch it or influence it in any way, remotely or otherwise. Teams may not alter the testing platform in any way. Completed vehicle must remain in motion during the testing phase. If it fails to move in any direction for more than 1 second, testing will be considered complete and a final test time will be recorded. If the vehicle falls from the testing platform at any time during the testing phase of the contest, final test score will be recorded. In the case of this class, we will use a 2-meter diameter circle or a 1-meter radius circle. And if you're doing this, not with us, you can use some tape on a floor. 2 meters is about 6.5 feet. So you can go ahead and make your own testing circle, tape it out on the floor. We're not going to let the cars fall off the platform. Teams will have 3 trials on the testing platform. Okay, so you get to try it 3 times. And the highest time will be used as the final score for the team. Teams will not allow to be making significant modifications to the vehicle during testing. Each team will have only 3 minutes between trials on the testing platform. Not making significant modifications, in other words, you'll not be able to add parts, you'll not be able to remove parts, you'll be able to fix anything that maybe went wrong with it, something slipped and came loose or anything else. And the teams will be required to submit vehicle sketches labeled prominently with each team name prior to testing. I'm going to modify these rules somewhat. Modifications will be, you will only be allowed to fix things that break on your car. Right? So modifying will be only if the car breaks in some way. Otherwise you won't be able to do anything to it. You'll not be required to just submit vehicle sketches. I want you to go through the entire process. Okay? So you're going to submit to me, just like you've done on previous projects, you're going to submit to me 3 possible designs. A feasibility and analysis study where you're going to talk about the different things you wanted to be in the design of your car and how each of these 3 designs met those criteria, and you're going to grade them just like we did in Chapter 5 here. You're going to have a chart that says the most important thing is that the car takes the longest amount of time possible getting out of the circle. And that's going to be my most important thing. I'm going to rate that at a 10. And each of your designs will have a rating for that. This car is an 8 for that design, this car is a 9 for that design, or for that criteria, and so on. And you're going to grade them. Okay? And then you're going to choose the best design, and then you're going to do a detailed drawing of your best design on graph paper to scale using the parts that you have in your kit. And then you will submit all of that to me. Right? Once you've submitted that to me, then you can start testing your car. Which means I would recommend that you have that submitted by Wednesday. If you don't have it submitted Wednesday, you're going to be in trouble because you'll only have the weekend, because then you'll have to submit it to me Friday. But I would recommend that you get that stuff submitted as soon as possible. So I want your 3 possible designs and your study, your analysis of what is going to be your best design according to a chart of criteria that you choose, right? And you're going to include some of these things, right? You're going to include, for example, something that doesn't stop for more than a second, right? How important is that to you? Maybe it's not as important as it going as slow as possible, right? Or taking as much time as possible. But, I guess that's about all I've got here. The teams, though, that's one other thing. The teams will not be teams, they will be individuals. That's the other difference that we'll do. Since we only have 4 people in this class, we will not split into teams. We will do individual cars, and you will turn these things in individually. So, what are the rules so far that I've got for you that are different? Rule number 1, for this particular project, is it's going to be a 2-meter circle, 2-meter diameter circle, right? So that's one thing that's going to be a specific thing about our competition that's not labeled here. Number 2 is that you will use parts in your kit, from the kit, and you want to use as little as possible. As little possible, right? Number 3, you're going to use the design process. Right? You're using the design process. Number 4 is you're going to turn in 3 possible designs, 3 designs with analysis. And a final drawing of the one that wins out in the analysis process. Okay? Before you start testing. Don't necessarily need to do it before you start building, but you certainly should do it before you start testing. And then you can start testing your car. For those of you here in North Platte, you're more than welcome to come in and test the car in my room if I'm here. If I'm not here, then of course you can't test it in my room. But if you set up an appointment with me, I can try to be there when you want to be there. I will send out a little page to you by email so that you all get it in email with these things in it and this page here so that you can all have this information. And we have 1 week to do this. So a week from today will be the day that we actually test them in class. Do you have any questions? No questions? Okay. I will let you have the rest of the time today to go ahead and get started on this process. And if you have any questions, I will be in my office. On Wednesday, I will be here to accept any of your drawings and analyses of designs if you want to turn them into me Wednesday so that you can begin testing. And if you just want to keep working on it on Wednesday, that's fine. I will be here and available to you. Same thing on Friday. I will be here available to help you out with your testing, for you to turn in your analyses or your drawings, your designs. And then next Monday, we'll test our cars. This is the slow car contest. So check your email for this. There's something that they include here, this list of materials that I'm not going to include, just so you know. Some of these things will not be available to you. Things like mouse traps and electric motors will not be available to you. I will also not provide batteries. But you have what you have in your kit, and you may also take apart your last project if you want to use it. You can use parts from the bridge if you want. Up to you. Here they say the team scores are determined by the amount of time the vehicle remains in motion. That will be part of the score. It'll essentially be half of it. Well, about a third of it. A third of it will be participation. So if you get things turned in and you bring a car, you'll get about a third of the grade, about 40% of the grade. The remaining 2/3, about 60% of the grade, will be 30% for your paperwork, all your design, and 30% for your performance in the end. So, and in that performance part of it will be efficiency. So the less parts you use, the simpler the car. Fewer parts that you use, the efficiency will be part of your performance. And so that I'll include that all in the sheet that I'll send out to you so that you have all those details. If you have no more questions, I'm done for today, and we'll see you when we see you as you're doing this project.